Welcome to This Explainer. I am so incredibly excited to guide you through today's topic. We're going to explore the absolutely mind-blowing invisible world of atomic motion. If you've ever stopped to wonder what's actually happening down at the fundamental level when ice melts, when water boils, or say when a log catches fire, well, you are in the exact right place. We're going to break down the absolute basics of physics and state changes, making it super easy for beginners, and we'll do it all by visualizing things you literally can't see with the naked eye. Let's get right into it.
I actually want to start off with a somewhat dramatic hypothetical. Just imagine, for a second, that some massive cataclysm occurred and absolutely all scientific knowledge was about to be destroyed. If you could pass just one single sentence onto the next generation, one statement holding the absolute maximum amount of information in the fewest possible words, what would you say? This is kind of the ultimate question to kick off our journey today from the macro down to the micro.
Well, the answer to that really profound question is known as the atomic hypothesis. It goes like this. All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. It sounds simple, right? But this single sentence holds just a staggering amount of information about how our entire world operates. That is, if we apply just a little bit of imagination and critical thinking to it.
Now, you might be wondering, how do we actually know this? Well, it's really important to remember that scientific knowledge is essentially this constantly expanding map of approximations. The core principle of science is that experiment is the ultimate sole judge of scientific truth. But here's the catch. Experiments only give us hints. They don't give us the whole picture. We have to use our imaginations to guess at the wonderful, sometimes really strange patterns beneath it all. And today, we're definitely going to use our imaginations heavily to visualize these invisible truths.
Okay, let's dive into this. Literally, we're going to take a mental zoom sequence right into a tiny quarter-inch drop of water. Step 1, looking closely, it just looks like smooth, continuous water, right? Okay, step 2, let's magnify it 2,000 times. Suddenly, the drop is 40 feet across, and you might actually see tiny paramecia swimming around in there. Step 3, magnify it again by 2,000. Now it looks like this teeming, completely chaotic crowd at a massive football game. Finally, step 4, we magnify it another 250 times. That is 1 billion times total magnification. And suddenly, we've arrived in this wild world of incredibly dynamic, bouncing atoms.
And this is what that water looks like magnified 1 billion times. Notice those black blobs? Those are oxygen atoms. And the little white blobs tied onto them are hydrogen atoms. Each group, 1 oxygen, 2 hydrogens, makes up a single water molecule. But please do not look at this as just some static drawing. You really have to imagine this as a highly dynamic, totally chaotic, jiggling, twisted cluster. They're constantly bouncing and turning, attracted to each other so the liquid doesn't just fall apart, but immediately repelling if they get squeezed too close together.
So, here is a really, absolutely crucial point to wrap our heads around. Heat is literally just jiggling motion. What our crude human senses perceive as heat is actually just the microscopic jiggling of all these atoms. When we crank up the temperature of that water, we are quite literally just increasing the motion and the speed of those jiggling particles. As they shake more and more violently, the volume between the atoms actually increases. Now, what happens if we keep cranking up that heat? Eventually, the pull holding those molecules together just isn't strong enough anymore, and bam! The molecules completely fly apart. They separate entirely from one another, just bouncing around in absolute perpetual motion. Imagine walking into a room filled with thousands of tennis balls flying in every possible direction, constantly ricocheting off the walls. That continuous bombardment against the walls, that is exactly what creates the jittery force we call pressure.
And this brilliantly illustrates the total extremes of physical states. On one extreme, you have steam, separated molecules, bounding wildly, exerting all that jittery force or pressure. But then on the complete opposite extreme, we have ice. In ice, the molecules are locked tightly into a rigid, hexagonal crystalline array. The atoms aren't flying around freely, they have a very definite place. But, and this is key, they aren't perfectly still either. They still have some heat, which means they are constantly vibrating right in place within that rigid structure. So taking a closer look, here's a really great visual representation of that rigid, crystalline pattern of ice. Notice that hexagonal symmetry? That actually explains why snowflakes always have that beautiful six-sided appearance. But look really closely at the structure itself. Do you see all those empty spaces, those kind of holes inside the pattern? Well, when ice warms up and starts to melt, that strict organization breaks down. Those holes actually collapse, and the loose molecules fall in to fill the gaps. This perfectly explains that really weird, surprising fact of why ice actually shrinks when it melts into liquid water, whereas almost everything else in the universe expands. Now, before we look at some more complex processes, let's just ground ourselves in the sheer literal scale of what we're talking about here. Just how microscopic are atoms? We usually measure them in a unit called angstroms, but honestly, to really grasp it, imagine this. If you were to take a regular apple and magnify it until it was the size of the entire Earth, the atoms inside that apple would be roughly the size of the original apple. It is a completely mind-bending scale when you think about it. So, keeping that incredibly microscopic scale in your head, let's ask a really relatable, everyday question. Why exactly does blowing on hot soup cool it down? I mean, we've all done it instinctively since we were kids, right? But now, we're going to look at the actual dynamic atomic processes behind it to finally solve the mystery.
What's truly fascinating here is what's happening right at the surface of a liquid. A seemingly still glass of water or a bowl of hot soup is actually a microscopic battlefield. Molecules are constantly jiggling around in the liquid, and occasionally one gets hit with just enough extra energy that it gets knocked clear away into the air. That right there is evaporation. But at the exact same time, vapor molecules up in the air are constantly flying back down and getting trapped back in the liquid. If you have a closed container, the number of molecules leaving perfectly matches the number coming back. So to our eyes, nothing seems to change at all.
Let's break down the exact mechanics of evaporation to finally answer our soup question. When surface molecules get knocked away, it's because they've managed to accumulate some accidental extra energy. Because only the very highest energy molecules manage to escape, the ones left behind in the bowl end up having a lower average motion than before. And remember what we said earlier? Lower motion literally means less heat. The liquid is sweating away its hottest atoms. So when you blow on the soup, you're actually blowing away the water vapor hovering in the air right above it, preventing those high-energy molecules from bouncing back in and bringing their heat with them. You're maintaining the evaporation, and boom, the soup cools down.
Section 2. Building complexity, from physical to chemical processes.
All right, let's move on and see how this all builds up. Moving from simple physical phase changes, melting, boiling, evaporating, where molecules just move around but don't actually change who they are attached to, we see a massive, massive leap in complexity. Take a look at the contrast here. On the left, we have a relatively simple but highly violent reaction, carbon burning an oxygen. Oxygen molecules rush in, grab onto carbon atoms, and fly off as carbon monoxide. But on the right side, we see something entirely different. That incredibly sprawling map, that is the actual molecular structure for the odor of a violet. It is a staggering, highly complex, three-dimensional biological arrangement of carbon, hydrogen, and oxygen atoms.
This really highlights the incredible power of atomic rearrangement. You see, atoms are super picky. They have very specific preferences for who they partner up with. When carbon and oxygen meet, they don't just gently connect, they snap together with tremendous vengeance and commotion. That massive sudden release of motion energy is exactly what we see and feel as heat and flames. Conversely, those monster molecules we talked about, like the odor of a violet, they don't burn like that. Instead, they form delicate, exactingly precise 3D arrangements. Chemists map out these completely invisible structures by mixing different substances together and doing some fantastic, mind-boggling detective work to see exactly how the atoms rearrange themselves.
Now at this point, you might be wondering, okay, but how do we really know all this for sure if atoms are way too small to see, even with a light microscope? Well, one absolute game-changer piece of evidence is called Brownian motion. If you put tiny but still visible particles in water and look at them through a standard microscope, you will actually see those particles constantly jiggling around in this random, irregular fashion. It's literally exactly like watching a giant pushball on a field being knocked around from all sides by an invisible, jostling crowd. That visible jiggling is direct, undeniable evidence of the completely invisible bombardment of moving atoms.
So what does this all mean? We'll end today's explainer on a really profound, almost philosophical question directly from our source material. Think about this. If a pile of identical atoms can make up a rushing waterfall, or a block of rigid ice, or a violent roaring fire, what happens when you make an arrangement that is continually changing, constantly evolving, not repeating, and built out of many different kinds of atoms? Is it possible that the thing walking, talking, and looking right back at you in the mirror every morning is really just a great glob of these exact same atoms in a staggeringly complex arrangement? It kind of leaves you marveling at the sheer complexity of life.
knowing it's all built entirely from simple jiggling atoms. Thank you so much for joining me today to explore this absolutely incredible topic.